Good afternoon, everybody, or good daytime or nighttime, depending on your location. Today I am going to present you heat sources in Norway and their thermal effect. I am definitely sure that most of you are not interested in the Norwegian specifics, but everything what I will show you in my presentation can be used in your country as well, since geology and tectonics is always similar. Okay, I will start with the regional scale major heat source, and I will illustrate this for the North Atlantic region by using these super deep boreholes from Sweden, Finland, and Russia, together with two deep boreholes from Iceland. Here you can see the location of these Fennoscandian boreholes and Icelandic boreholes. And I think it's obvious that temperature is much lower in central eastern Fennoscandia compared to Iceland. And the reason is quite simple actually. This is related to thickness of the lithosphere, because lithosphere is more than 200 kilometers thick below central and eastern Fennoscandia, and very thin below Iceland. And actually, in addition, there is magmatic activity along the mid-Atlantic ridge, which actually forms new lithosphere even now when I'm speaking to you. And actually, Norway has own small island. Possibly it can be interesting for somebody. It is Jan Mayen, which is also located quite close to mid-Atlantic ridge. It's kind of a small-scale island, but with conditions of thermal conditions of the subsurface very similar to those what we have on Iceland. Okay, base of the lithosphere or thickness of the lithosphere, distance from the surface to the molten upper convective mantle can be considered as a kind of a factor which control subsurface temperature distribution at the regional scale. Therefore, internal heat of the Earth can be considered as a major heat source. And now I will illustrate the influence of this heat source or influence of the thickness of the lithosphere to temperature in Norway. Here you can see the location of all deep boreholes in Norway for which we have temperature logs. Here you can see these temperature logs. Don't try to understand. It's a bit chaotic and too dense. Even I tried to highlight them by different colors, but still. What I would like to tell you is that the deepest borehole in Norway, what we have, is located on Svalbard, and this borehole is called Grumant 1, which is more than 3 kilometers deep. This one has been drilled by Soviet geologists for oil and gas prospecting on Svalbard. But on the Norwegian mainland, the deepest borehole is the Bjerkreim borehole, this one. But the problem is that this borehole was collapsed at the depth around 1 kilometer, and therefore we are not able to measure temperature down to more than 2 kilometers depth, where this borehole bottom is located. Yeah, it can happen, but it's unfortunately happened with the most deepest borehole on the Norwegian mainland. If I will compare the Norwegian boreholes or measure temperature in this borehole with the super deep boreholes from central and eastern Fennoscandia and temperature data from Iceland, we will already see that temperature in the Norwegian boreholes is slightly higher compared to central eastern Fennoscandia. It's especially visible when I zoom in the image with temperature logs. Of course, we still have some low temperature, but actually what you should be aware that temperature within the uppermost part of the column, super deep borehole, is strongly disturbed. This means that it should be much lower, something like we have here. But in Norway, in addition to this onshore borehole data, we also have quite plenty of oil and gas exploration wells offshore, location of which you can see here. And if I will plot them together with the onshore boreholes, then this transition from the thick and cold lithosphere in central eastern Fennoscandia through the Norwegian continental shelf towards the mid-Atlantic ridge is even more visible, as you can see here. And finally, I would like to show you these two profiles. It's modeled profiles with temperature distribution. And as you can see here, it's clearly visible the temperature increasing towards the ocean. Some of you can tell that this is possibly due to blanketing effect of thick sediments, but it is, of course, there, but anywhere in place where we don't have sediments, temperature is still growing. And this actually distribution of temperature is quite well calibrated by temperatures measured in deep wells offshore and deep boreholes onshore. This means that it's relatively realistic, I would say. And if I will continue to show some example of influence of thickness of the lithosphere on subsurface temperature distribution, I would like to show you, first of all, the temperature from Svalbard. Here you can see the temperature logs which have been measured on Svalbard. They are highlighted by blue color. It's obvious that this is actually the highest temperatures, because you should not consider this upper part, because in this case it's affected by paleoclimate and also by present-day climate, because here you can see the some intervals are related even to the permafrost when temperature is below zero. But with depth, we see that here we have the highest temperature, and the main reason is just location of Svalbard, which is located very close to the mid-Atlantic ridge, and lithosphere is relatively thin below Svalbard. And another example is from northernmost Norway. It's actually opposite side of temperatures measured in Norway. Here we have the lowest temperatures. And again, the main reason is thickness of the lithosphere. One of the main reasons, I would say, because of course there are some other factors which control temperature in these boreholes, but one of the main reasons is related to very thick lithosphere, which is more than 200 kilometers thick in this area compared to Svalbard, where lithosphere is thinnest. All what I explained you so far is quite well illustrated by this recently actually constructed map with geothermal gradient over the whole Fennoscandia and partially over the Norwegian continental shelf. It is obvious that thermal gradient is highest towards the ocean and lowest at the regional scale within central and eastern Fennoscandia, with some local maxima, which is actually related to blanketing effect of sediments in this area, of low thermally conductive sediments, and with this quite well visible geothermal low, which I called actually like Olgort geothermal low in southwestern Norway. And the reasons for this, some possible reasons for this geothermal local actually compared to the regional scale pattern, geothermal low, I will explain you further during my presentation. Okay, local scale heat flow sources. Now, this I will show you by using data from the Oslo region. You can see it's a relatively small area with quite similar geological and tectonic settings. But in this small area, we have quite wide range of the measured temperatures, and the reason is related to content of radioactive elements. This I will illustrate you by use temperature log from these two boreholes, the Gardermoen borehole and Arvalskogen borehole. Here the details. As you can see, temperature in the Arvalskogen borehole is higher than that one in the Gardermoen borehole, but the distance between these boreholes is slightly more than 100 kilometers. It's also quite interesting. The reason is it's actually quite simple. As you can see here, the content of radioactive elements in the case of Gardermoen borehole is relatively low, and the calculated or infrared radiogenic heat production is also around 1 or even lower than 1 microwatt per cubic meter. In contrast, in case of Arvold-Skogen borehole, content of radioactive elements is much higher, I would say, and the calculated radiogenic heat production is also quite high. And the difference is more than 6 times. As you can see here, if you will take just the average values for these boreholes. This is 0.7, and here we have 4.3 microwatt per cubic meter. Actually, this is one of the reasons why temperature is higher in this borehole compared to this one. And I think it's obvious that radioactive decay produces heat, and this internal crustal heat can disturb or add to the heat budget coming from the Earth's interior. Here you can see a map with average values of radiogenic heat production assigned for different lithological tectonic units in Norway based on geochemical measurements. And as you can see, the range of radiogenic heat production is quite high, from almost 0 to more than 6 microwatt per cubic meter. And this always can be considered as a local, important, and still major heat source. It is not only important for onshore areas where we don't have sediments and we have thick crystalline rocks, but it's also important for the sedimentary basins offshore, because all this temperature, it's model temperature, but it's quite well calibrated, also has input from decay of radioactive elements within the sediments, because here you can see the radiogenic heat production for different layers, and the range of radiogenic heat production is almost from around 0 to around 2 microwatt per cubic meter. And if we will consider the thickness of sediments, which is locally up to 20 kilometers, but on average can be like 8-12 kilometers, these thick sediments with these values can produce quite a lot of heat, in addition to heat coming from the Earth's interior. Okay, decay of radioactive elements can be considered as the second major heat source. Now, additional heat sources which are existing, but influence of them is actually not so high. The first one is related to seismicity. Here you can see some of the earthquakes in Norway. It's mostly microseismicity, by the way. Each earthquake along the fault produce movement. Actually, if you have movement, especially at high depths with high pressure, then of course it will be heat due to friction also produced. This heat in general is not so high for the regional scale and can be even neglected, but at local scale along some faults or long active faults, it can be quite important, because during this movement of the blocks, friction can produce temperature which is high enough even to melt the rocks locally. But of course, at the regional scale, this influence can be neglected, or it's actually quite difficult to estimate, to be honest, to estimate correctly, properly. Okay, additional heat source is first one friction related due to seismicity, and then exothermic chemical reactions. Of course, the well-known reaction of oxidation of pyrite can be considered as an example for heat-producing oxidation. But of course, pyrite is not, or other metals, they are not so frequently located, or they don't have large size, and therefore they cannot really consider it as a regional scale or even local scale. heat source. But still, here you can see the location of all Norwegian mines, in most of which metals are present. This means that locally in some mines, especially when these deposits are open for air or water enriched with oxygen, we can have this increasing of temperature due to oxidation or this exothermic chemical reaction. But of course, this effect is really very, very local. However, in case of serpentinization, this is another example of exothermic chemical reactions when olivine or pyroxene together with water can produce serpentinides, hydrogen, methane, and heat. This is actually important for us. And this actually already quite significant because thickness of peridotites which contains olivine or pyroxene can be quite significant, and therefore in places where these peridotites can be reached by migrating from the surface seawater, this actually in case of Norway can happen along the continent-ocean boundary here, then temperature can be really significant and can even have already significant local scale and possibly even regional scale effect. For instance, here in some of the boreholes we have relatively high temperature, which can be at least partially explained by serpentinization at the depth. Because, for instance, in one of the boreholes we have thermal gradient which is around 60 degrees per kilometer. It's obviously due to fluid flow, and this hot fluid can be created due to serpentinization. Then, additional heat source also can be related to exothermic chemical reactions. Now, disturbing factors. First of all, paleoclimate. As you can see here, during the last glaciation, most of the Fennoscandia was covered by ice sheet, but during some time intervals, a large part of Norway was free of ice. This means that it was really affected by those atmospheric cold conditions, and temperature of the air could be lower than minus 100 degrees, similar to what we have now in Antarctic. And this very low surface temperature, of course, would cool down the subsurface. As you can see, temperature normally can be more than 20 degrees compared to the interglacial and glacial maximum, or even almost 30 degrees in case of Greenland. And this effect I would like to illustrate you by using this super deep borehole from Russia. It's a Kola super deep borehole. By using this uncorrected heat flow density. Why it is important? Because according to all theoretical calculations, the thermal effect of the most significant paleoclimatic thermal effect usually goes not deeper than 2 kilometers, depending on, of course, thermal conductivities. In case of this borehole, I think it's obvious that uncorrected heat flow density somehow increasing towards the depth of 2 kilometers and then clearly decreasing. This is actually paleoclimatic effect due to cold temperature during the last glaciations. Not only one glaciation, actually. Okay, the first disturbing factor is paleoclimate. The another one I will show you by example of Western Norway and the Nordland area. Here you can see the highlighted temperatures from the Nordland area and here from Western Norway. But the most important, this map, where you can see average atmospheric precipitation over the Scandinavia, and the highest precipitation is concentrated in Western Norway and in the Nordland area. And of course, this precipitation with this very steep topographic gradient can go through the fractures to the subsurface. I mean water from this precipitation. This I will illustrate you by an example from the filling down borehole in western Norway, where we measure temperature down to depths of slightly more than 500 meters. But what you can see here is the anomaly, and this anomaly is related to groundwater flow at this depth. Actually, originally we wanted to drill it a research borehole. We wanted to drill the borehole down to almost 1 kilometer, but at this depth, slightly deeper than 500 meters, rocks are really almost crushed. I mean, it's strongly fractured bedrock. And we didn't have budget to cement them because in the depth interval is really huge with these crushed rocks, and it's totally filled with water and active groundwater flow. Is there active groundwater flow deeper? It is still open question, but rocks are really fractured, also at depth is down to 2 kilometers according to the borehole data. This actually gives us kind of an assumption that this moist air from the Atlantic Ocean can be stopped by relatively high Scandius mountains, which are locally more than 2 kilometers high. And then all this water, which goes from the atmosphere, can theoretically go through fractures and cool down the subsurface. Of course, energy cannot disappear. This means that all this heat can be moved by advection towards the sedimentary core. However, we don't really know where this heated water outflow. It is still open question. Okay, groundwater fluid flow is another disturbing factor. And now uplift and erosion or subsidence and deposition. Here I would like you to explain what we should expect in terms of temperature during erosion and deposition. Before erosion, you can see here, isotherms are sub-horizontal. It's a simplification, of course. They are not sub-horizontal in the reality, but for understanding the process, I made this simplification. And what we will have during the uplift, of course, these isotherms will go up in the place of uplift and will go down in the place of subsidence. This is actually heat advection by solids, because heated rocks will go up and cooled rocks will go down. And immediately after erosion, when this area is still not in thermal equilibrium, but for thermal equilibrium we need at least, to be close to thermal equilibrium, we need at least around 15-20 millions, and to get thermal equilibrium we need actually around 50 millions years. And most or part of this uplift and erosion occurred during the Quaternary or during the last 2.5 million years. And this means that in these areas which were uplifted and eroded during the Cenozoic and especially during the Quaternary, we should observe positive thermal anomaly where upper crust was uplifted and eroded, and negative thermal anomaly in place of relatively quick deposition of this eroded material. This can be illustrated by thickness of the Quaternary, which is locally more than 2 kilometers thick. And can you imagine all this deposition occurred during the last 2.5 million years. And I calculated actually the thermal effect of Cenozoic including Quaternary erosion and deposition for these two areas. And as you can see, positive thermal anomaly is more than 10 degrees locally in the areas which were uplifted and eroded. And actually it can be around minus 30 degrees in the areas which were subsided and quickly covered by thick sediments. Okay, another disturbing factor is uplift and erosion or subsidence and deposition. Another important controlling factor of this temperature distribution, for instance, offshore, this is actually model temperature, but still It's relatively well calibrated by some temperatures measured in the oil and gas exploration, boreholes or wells. And here you can see the total thickness of the sedimentary core. The correlation is not perfect between temperature and thickness of the sedimentary core. The reason is quite simple, because here seafloor topography or bathymetry plays also a role. For instance, in this area we have very deep bathymetry into this area as well. But in case of thickness of Cenozoic, the correlation is much more better, as you can see here. And here, I mean, thickening of the Cenozoic coincides especially with increased temperature. The reason is quite simple, because Cenozoic sediments they are not so strongly compacted and still porous, containing a lot of water, and therefore thermal conductivity of the sediments is relatively low, and the blanketing effect is quite well visible at the depth of 5 kilometers. Okay, another disturbing factor is thermal conductivity, which is especially visible in case of blanketing effect of thick young sediments. And the last one is related to upper mantle low velocity anomalies. Of course, you can tell me that this upper mantle low velocity anomaly can be related to changes in composition of the upper mantle. But the main point that this upper mantle low velocity anomaly in case of below western Norway goes deeper towards the convective mantle. And if we have mantle anomaly, low velocity mantle anomaly in the convective part of mantle together with the lithospheric mantle, this actually allows us to suggest that this is related to temperature or increased temperature. Here you can see the configuration of the low velocity upper mantle anomaly below western Norway for S and P waves at depth of 50 kilometers, and as you can see, it's quite strong. And if it is related to temperature, then it somehow should be reflected in the crust as well. And therefore, additional factor can be related to upper mantle thermal state. In summary, what I can tell you that major heat sources is related to internal heat of the Earth everywhere on the Earth, and then decay of radioactive elements within the lithosphere or mostly within the uppermost crust is another important factor. And then additional heat sources can be related to friction during seismicity or exothermic chemical reactions. And thermal effect of exothermic chemical reactions is especially important in case of serpentinization offshore along the continent-ocean boundary. And important disturbing factors are related to paleoclimate, groundwater flow, uplift and erosion or subsidence and deposition, thermal conductivities, and thermal state of the upper mantle. Thank you for your attention.